Welcome class. This recording will be focusing on the problems related to MOSFET material that I covered in my last lecture. So in chapter 5 in the textbook, as I had suggested or mentioned that I would cover, I covered the first three topics, section 5.1, 5.2, 5.3 in the last lecture. So we'll do problems related to this. I hope you still remember what we did last time. I introduced the MOSFET to you. We talked about the three terminals, the gate, the source and the drain, the current flow in an NMOS FET, and then the opposite, the PMOS FET, the gate to source voltage, the drain to source voltage, the value of the current ID, a couple of formulas that we looked. We also talked about the triode region, where the gate to source voltage is small, and then the saturation region, the gate to source voltage is gradually increased. Actually, the drain to source voltage is gradually increased. So we talked about that. We also looked at some models, large signal models basically, and then we mentioned briefly biasing, right? How to find a particular combination of drain current and drain to source voltage that gives us a saturation region operation. So we did all that. So let's begin this session by looking at some examples and problems so that we can put some numbers to all the material we covered last time. So the first example in your textbook is example 5.1, and I hope you can follow along as I talk about this. I hope not to spend too much time on the examples, but just to give you the broad steps, because you can certainly look through these at your own pace. But I will definitely cover the problems in a little more detail. So example 5.1 is a very basic example. A lot of this data, the physics of the device is given, and we are asked to find COX, which is the capacitance, right? And also this process parameter Kn prime. So that's part A. Part B, we are asked to calculate, we are given a particular DC current ID, and we are asked to calculate corresponding voltages, such as the over voltage and the gate to source voltage, etc. So this formula ID equals half Kn prime W by L, which is the aspect ratio multiplied by the over voltage square. You remember, over voltage is the difference between the gate to source voltage VGS minus the threshold voltage VT, right? This is one formula that's being used, and then part C is interesting because it is forcing us to look at the device with a low DS, small drain to source voltage. That is the it's operating in the triode region. So there we have said that the FET can be modeled as just a resistor, right? So the question is, if you want it to be a 1000 ohm resistor, the entire FET, then what values of GS and the VGS and V over voltage will help you get us to that 1000 ohm resistance. So those are the 3 or 4 parts, and let me quickly open up the my PDF version of the textbook to example 5.1. So hopefully you can also open it up. So part A says find COX. Now I don't think I talked about this formula and I hope not to have to do this ever again in the course, but there is a formula that connects that capacitance to something called epsilon Ox, which is like a constant, and then Tox. So these two factors together give you Cox. Generally, in most problems, we are just given Cox, so I didn't bother with it. But you can see how we derive Cox. Remember, it's not a capacitance, but it's a capacitive density. That means capacitance per area square, right? So you see how that's calculated. Then you see how this factor, the process parameter Kn bar, which is just electron mobility times Cox, you see how that is calculated. So that was part A. Part B, for operation in the saturation region, a certain current has been given, the current through the device basically. We generally show it as ID, but it's actually, ID or IDS, however you want to call it. It's related to the over voltage in this way, so you come up with the over voltage value. Once you have the over voltage, you know Vt is a constant. It's probably given somewhere here. Yeah, it's given as 0.7. So from there you can calculate VGS. Also remember the saturation condition happens when the drain to source is at least equal to the over voltage. The drain to source voltage can be higher than over voltage, but for the minimum to enter the saturation condition, you have this condition or this value where ds min equals V over voltage, which is also that same 0.32 which was calculated here. Finally, to find that RDS, which is the opposite of one GDS, which is transconductance, you use this formula, and to get to 1000 ohms, we end up with an over voltage of 0.52, which then gives us VGS by using this formula 1.22. So hopefully with this example you're able to now for the first time use all these values, right? All these numbers, high, low numbers, such as Kn prime, Vt, Cox, right? All of these values. And then the aspect ratio, width by length, because that is given here as generally width by length is given in this form. Okay? All right. So I will move on. I'm going to minimize this and I will move to the next problem, which is from the back of the chapter, and it's problem 513. So a similar problem, it talks about an n-channel device, that means an NMOS device. These values are given, Kn prime again, Vt is given, W by L is given. So it's similar problem. So the device is to operate as a switch for a small VDS utilizing a control voltage VGS in this range. So when they talk about a switch, basically what it means is you have to find that same resistance RDS that we saw in the previous chapter, and we have to find VDS. So basically that's what is required, right? So how do you do that is the question. And the last part of this is a little bit funny. So you're getting a switch with this, right, certain resistance. To get that same switch using P channel device, what size difference would be necessary, right? What different W by L would be necessary is what he's asking. And the reason we are asking this question is because we know that the whole mobility mu p is only is about 40% of the electron mobility. So given that difference, how do you still get the same resistance? Obviously you have to play with the area and the width and the length to get that. Okay, so that's the question, and so I will go to my PDF. You're all used to my PDF by now, and where I solve these problems by hand, so that I have a number of steps that I write so that you can follow along and better understand how the problem is solved. Okay. So basically we are given all these values including Kn prime, Vt, the aspect ratio, a certain gate to source voltage and the corresponding drain current also. So pretty much a lot of information is given and so how do you find this resistance? So this resistance RDS is VDS by IDS, one of the formulas. So you can write that in this form. So you end up with 1 by this, which actually is JDS. So we didn't have to go through all this. But anyway, these values are all given. So I find RDS to be 116 ohms. So once you know RDS, you can find VDS, which isn't given. Only VGS is given. So we can find the drain to source voltage using this equation. There's other ways to find it, but this is one way to find it. Okay. So that was part A, and we get 116 millivolts. Part B is where we have to say if you want a P MOSFET, then what will be the aspect ratio. So here, remember, the aspect ratio is given as 20, right? Width by length is 20. So if you take the ratio of these values, because this is RDS, right? This is a relationship for RDS in addition to other things in the denominator. Assuming everything else is the same, then RDS depends on this kind of relationship. So if you take the ratio of that, you end up with the fact that the ratio of the whole mobilities is 2.5. So the ratio of the aspect ratios will be 2.5 times that value of the one for the N MOS. So we are trying to find the P MOS value. So you multiply this 2.5 by that N MOS value and you get the new aspect ratio. Okay. So I hope that was clear. I will minimize this and move on to some more problems. So by the way, I was on slide 19 and 20 if I didn't mention it in the already. So we are at 21, moving on to 22, 23, 24, 25. You see all these curves. 26, 27, 28, 29, 30. Okay, 31. Finally, we have another problem. So this is a problem not from our textbook, from somewhere else, but again I felt this was a good introduction to this topic about the ID VGS characteristics. Okay, so the problem is, I call it problem finding ID. So you can see that the circuit is drawn in this way. Now you've seen BJTs, NPN, PNP transistors drawn this way, but this probably is the first time in this chapter for FETs we are seeing a circuit drawn in this way. So I thought this would be a nice introduction, because from here on all of our circuit problems will look like this. So in this circuit, what is given? We are given biasing voltage, a battery voltage actually 1.8, connected through a drain resistor to this PNP, not PNP, but NMOS circuit. Now NMOS devices are shown with an M. You probably remember transistors, BJTs were shown with a Q. It's just a practice. So M1 is the device. We have a well biased device. We have a gate to source battery 1 volt, which is also the gate to source biasing voltage, and we have a battery to help bias the drain to source junction also through a resistor though. Okay, so that is new. So that is the condition, and of course the source itself is grounded, which is normal practice, and we are given the aspect ratio here, W by L is 2 by 0.18. So what is he asking us? Calculate the current ID. Okay. So if we know that this is in saturation, or we don't know, we can try to find if it is in saturation, then we have a formula. If it is not in saturation, if it's in the triode region, we have another formula. So we'll use one of those formulas. He's also giving us this mu n times COX. That means that factor Kn is given, so that helps. And then Vt is also given. Okay. Then there's a part B. It says if the gate voltage increases by 10 millivolts. See, right here we are given a gate voltage of 1 volt. Now he says gate voltage increases by 10 millivolts, so that's about 1%. What will be the change in the drain voltage? That means the voltage at point X, which is the drain voltage. Okay. All right. How do we solve this? Let me open up my PDF again and go to the top of page 2 of my PDF. So here we have the problem, again problem finding ID. All the data that's given I've shown here. I don't think I've shown anything new here. Maybe I've shown that there is an ID, that is the current in the device, begins from here and flows here. X is a point. It's actually the drain voltage Vd, but we just let's pretend it's X, and then I show the three terminals, gate, drain, and source, and you see the plus 1 volt. Okay, so one way to solve this problem, to find ID, which formula to use, right? So one way that textbooks teach us to do is to just assume it's in saturation and then double check later on, once you find the drain current, whether it's really in saturation. Okay, so assuming it's in saturation, this is the formula, and so we come up with 200 microamps. All the other stuff is given, right? VGS is given, which is this voltage 1. Vt is given, which is the threshold voltage is 0.4. So if you put all that, you get 200 microamps. So now we have to check for saturation. That is, find the voltage at point X, which will be VDS, and check if VDS is greater than V over voltage, which is VGS minus VT, right? That is the condition. It has to at least be equal and maybe greater than. Okay, so how do you find Vx, which is VDS? It's by KVL, right? So you write the equation KVL for this. You're used to that method now, I hope, because we did it for BJTs. So same method, we use KVL for that branch, and so Vx comes out to be the source voltage minus the voltage drop across the RD, so you come up with 0.8. Now remember, here we call this voltage VDD, the battery. In BJTs we call that the VCC, remember, collector. Here it's the drain, so we call it VDD. Okay, so we came up with Vx or VDS to be 0.8. So 0.8, is it greater than VGS minus VT? Yeah, because VGS minus VT is 1 minus 0.4 is 0.6. Hence, we say that VDS, the device, is in saturation. So that is one part. The second part was if VGS increases to 1.01 volts, right? We slightly increased it by 10 millivolts, right? This portion. So once that becomes 0.01, then we can repeat this whole thing. We first find the current ID, right? We have to find the current. This goes up slightly. It goes up to 206.7. I'm not showing the steps, but I'm just showing you the result. And so Vx becomes 0.766. Okay. So what is the conclusion? So by raising the gate to source voltage by just 0.01 volt, right, we actually raise the delta on the output. The drain voltage is 0.034. So you can see it's about 3.4 times gain, right? So even though we are not studying amplifiers yet, that is where we are headed, right? So this example is trying to show you the gain properties or the gain ability of the device. Okay, so that hopefully is clear. I have to move along. We always run short of time. So from moving on from slide 31 to slide 32, where we again deal with an example from the textbook. So this is example 5.2, and it has three parts. It's giving us the physics detail of an NMOS transistor. So there's a length, there's a width, COX is given, mobility, electron mobility mu n is given, and then VTN. This is your threshold voltage. Like I said, sometimes they'll give you the N, sometimes they don't, but normally N means NMOS, P means PMOS, right? So watch out for that. Then what are we asked to find? Find the VGS and a VDS that result in the MOSFET operating at the edge of saturation. So that means it is at saturation, meaning it's at a voltage where VDS is just equal to V over voltage, right? That is the edge of, that's the beginning of saturation for an NMOS. And he has given us the ID, so that helps. Next, find VG. If VGS is kept constant, find VDS that results in a different ID. So this was 100 microamps, now he's dropping it to 50. So what change in VDS is required is part B. And then part C, he starts to begin looking at it as a linear amplifier, the same thing that I just did in the previous example. And so he says we are in saturation, and so let it be operating in saturation with VDS is 0.3. Find the change in ID resulting from VGS changing, right? Previously we changed from 1 to 1.01, remember? Here he's saying go from 0.7, add 0.01 and take out or subtract 0.01. So this is your kind of a signal, right? Plus or minus, and tell him what the change in ID is. So he's still not asking us for an output voltage change, but he's asking us for a current, output current change. Okay, so you can see how to solve this. I don't want to spend too much time on this. This is 5.2, so let me get to 5.2 in the textbook. Okay, this is 5.2. So we have part A, part B, part C to solve. So the first thing he does is to find this process transconductance parameter, which is this Kn prime. Then he finds the transistor transconductance parameter, which is Kn. This is just straight manipulation of all the data that's been given. So we have this formula. Now, I mean these values. Now you can use the transistor operation in saturation formula, so to find the over voltage, right? So the current is given, find over voltage, which is 0.22. Once you have the over voltage, you know that that's connected to the VGS by this relationship, so we have the VGS. And since the operation is the edge of saturation, the drain to source voltage will be that over voltage value, which is 0.22. For the next step, he says find a different VDS, right? What is the part 2? Part 2 says if VGS is kept constant, find VDS that results in ID equals 50 microamps. So same basic procedure. We have this formula again, this formula, right? We keep VGS constant, reduce the value, right? So we are not in saturation anymore. I'm sorry, we have moved to the triode region. So the triode region, you use a different formula, and again you come up with VDS. Unfortunately, VDS comes out to be in a square form, so you have to neglect one of these values. So he shows you how to neglect one and use the other, because a quadratic has two roots, right? Those two values. So you use one of the values, and that is shown, VDS is 0.06 volts. Lastly, the amplification business, right? So assuming it's in saturation, we have a certain ID for a certain over voltage. Now if you change the VGS, then over voltage changes, right? So you have a new ID, right, which is so previously it was 86 microamps, then it changes to 94.8 when the VGS goes high, and the VGS goes low, the ID also goes low, so because it's a linear relationship. So thus he's making the point that for a change of 0.01 volts, we dropped by 8.8 microamps, and for a rise in 0.01 volts we dropped by about minus 8.4 microamps. So this is just a preview of the small signal business that we'll study later. Okay, all right, so that was that problem that was on slide 32, example 5.2. So let's keep moving. Now we talk about channel length modulation, where we actually I put in some new material compared to what we did last time. I realized I missed a couple of formulas. This is a busy slide, but I have to bring in these two formulas. Lambda equals 1 by VA, or VA equals VA, where VA equals another VA prime times length. So these are all used in problem solving. So I thought I might as well bring these to your notice. You'll see how they are used in problems. I also brought this graph in because I think I probably missed it. But what this shows you is that we know in the triode region the value of the ID, the current in the device, goes up as you increase the drain to source voltage. You keep the GS voltage at a constant and you increase the drain to source voltage, current goes up. And then we thought it's always flat. In saturation, we thought that it doesn't increase. But the truth is, because of channel length modulation, even in saturation, ID continues to increase, maybe less here at the bottom, but for these values of VGS, the rise is pretty sharp. So that is something that is going to come up in problems. So I thought this slide is also important. So this is a new slide compared to what I showed you in my last recording. Okay, all right. So here's a problem 534 from the textbook, and here we will address pretty much all that stuff related to channel length modulation in saturation, using the fact that the formulas are modified because of the values given to lambda. Okay, so it's an NMOS transistor. It has these values given. I think by now you're used to this. This is a new value, so you'll see how this is used in this formula to find lambda basically. And then we have ln W is given. So with ln W, first find VAN lambda, then find the value of the drain current that results when the device is operated, with so and so overdrive voltage, etc. So and then he also says find the value of RO, which is the output resistance with channel modulation. If you remember, this was in the model. Okay, and then there is one last part. If VDS is increased by 1 volt compared to the VDS here, we already have 2. Now if it's increased by 1, what happens to the IDS? So this is a little bit of the amplification issue. So lots of things in this problem. So let's see how we solve this. So let me go back to my PDF and look for problem 534, which is at the top of page 3 of my PDF. Okay, so all these values are given. First and foremost, we have to find lambda. To find lambda, we need to find this VA. To find this VA, we have to use this VA prime into L. So this value is given. VA comes out to be 30, lambda comes out to be 0.033. Why do we need lambda? Because in this current equation, right, for saturation, to find the drain current when the device is in saturation, we have to bring in this 1 plus lambda VDS to get an accurate value for ID. Otherwise, you are ignoring what's been given, right? So if you bring in this now, you come up with this 0.267 milliamps. Once you know this, you can find RO as 113 kilo ohms. This RO is output resistance, okay? This is different from uh, the triode region resistance that we just talked about earlier in this recording. That's a whole different animal, so don't get confused. This is strictly to help us model the output resistance when channel length modulation is in play, okay? All right. Now the last part that was asked is if uh, VDS, right, changes by 1 volt, what is the impact on the current IDS? And if you can do it both ways, right? You can use this formula, calculate IDS again, and then take the ratio. Luckily, since we found RO, you can use the simpler formula which says RO is also the change in voltage by change in current, sort of like Ohm's law, right? Voltage by current is resistance. So that gives you that change in current, the drain current, quickly as 0.008 milliamps. Okay. So I hope this was helpful. You might need to look at it a couple times to understand all the various steps, but I think it's a simple problem. Okay, let's move on to the next problem. I'm on slide 36, where we introduced MOSFETs, P-channel MOSFETs, PMOS. And yeah, here also I brought something new that I thought I should mention before we go to solving problems. Yeah, some points here about how these equations are written for the PMOS device. The equations are written in a way to avoid negative signs, right? Now we are comfortable with NMOS. Similarly, we are more comfortable with NPN. Once we have to go to PNP transistors, BJT transistors, or we have to go to PMOS, we tend to get a little bit confused because we spend so much time on the other one. So the point is, all the relationships are similar, but you have to watch out where the signs get turned around. So for example, with an NMOS, you know that the gate has to be positively biased. The collector is grounded, the gate is positive, the drain is positive. Not the collector, I'm sorry. I keep mixing it up. The source is grounded for an NMOS, the gate is at a positive, and then the drain is also at a positive, right? For a PMOS, it's flipped. The source is grounded, but here the ground is on the positive. So all the positive voltages in the circuit are at ground. So it's kind of reverse. We don't normally do it, but that's how he shows it here. It's not important, but remember. But anyway, in a PMOS, the the gate to source voltage is negative. Similarly, the drain to source voltage is also negative, okay, which is the opposite of what you see with a PMOS. But the equations are written in a way to avoid negative signs. Thus, while VTP is generally given to us as negative, remember VT, right? VTN was for NMOS. We are generally given VTP as a negative value like minus 0.4, but in the equations we just ignore the negative and just use the absolute value. That's why you have these straight brackets, okay? Also, instead of dealing with VGS and VDS, we just use VSG and VSD, which is the opposite of how it is normally used in equations. But by using SG, we can just use the positive, right, instead of negative. So basically VSG and SD are used rather than VGS and VDS, and then we stay with the positive. So you'll appreciate all this as we do some problems, but that is a point that I thought I should mention to you as we solve problems. One last thing I brought in here, this is not in, table is in your textbook, so pay some attention, understand all these relationships as we solve problems. But this particular equation was not here, but I thought I'd pull it here. This relates to what happens with a PMOS in where you're given channel length modulation. That means you're given this lambda and you have to use it to solve some problems. So to do that, you will need this formula, and so I thought I'd bring it in so you have all the formulas in one place. So basically you take this basic formula, this formula, and then you attach that 1 plus lambda by VSD, and you can find the drain current. Okay, so that is a summary of MOSFET, and so we come to a PMOS MOSFET. So we come to our first problem on a PMOS MOSFET. So this is from the back of the chapter, and here the circuit is not shown, so I put it together just to help us. It's not really a real circuit because there's no resistances and so on, but anyway, that's what he has given us, and so we have to work the problem. So here it is. So a PMOS transistor has all the usual values. It's given a VT, which actually maybe I should put that as VTP, right? Why it's not okay, maybe it'll come, or it'll crash the whole thing, hopefully not. Okay, anyway, yeah, there you go. So the VTP is given as minus 0.1, but then in our formulas we just take the absolute value. So you can say this VTP, the negative kind of gets dropped in this formula. So anyway, VTP is given, also lambda is given. Thankfully we don't have to derive this lambda. So the gate is connected to ground, as you can see here, and the source VDD is plus 5 volts. Okay, instead of saying 2, I should say is plus 5 volts. Okay, so find the drain current if VD is reduced in steps. So VD, which is also VDD, this VD. Okay, so okay, so if we go from a value of plus 4, slowly decreasing this value, okay, this is the drain biasing voltage. This is the source biasing voltage, the gate is at ground, and this is the drain voltage. And so he says the drain voltage is 4 initially, and then it starts to slowly decrease. So find the drain current at various points. Okay, so here is some of the formulas that we are going to use, and I also have some notes here. As VD decreases in the circuit, VSD increases, right? So if this decreases, this value source to drain increases, so current ID should increase in the triode region. The current also increases slightly in the saturation region due to channel length modulation. So this is what you should be observing, and let's look at the problem to make sure that's what we see. Okay, so I'll go to my PDF to solve 538, and here I show you the various steps. So as usual, we start with everything that's given, it's all here. So V gate is 0, V source is plus 5, right? That is here. V gate is 0, V source is plus 5 here, which is the source value, voltage value. And so what I calculate here is the source to gate voltage to be 5 volts, right, which is just the difference. So I calculate that and I keep it here. So we have to find that source to gate, which is 5 minus 0 is 5. We also have to find this over voltage, so we can use it in these formulas. So what is the over voltage? It's V source to gate minus that VTP, which is here, And remember, we drop the sign, so the negative goes away because we are dealing with a PMOS device. So we end up with overvoltage magnitude to be 4 volts. Now the formulas are: in the triode region, this is the formula; in the saturation region, this is the formula. In the saturation region, we also have to bring in that effect of lambda. Okay, so we are given 5 different values for this voltage, the drain voltage. Okay, starting with +4, then it goes to +2, then it goes to +1, goes to 0, and finally -5. At each of these, we have to first check whether the device is in triode or in saturation. Okay, so how do you do that? So we know to be in a triode, this V source to drain has to be less than that absolute value of the overvoltage. To be in saturation, it has to be either equal or greater. Okay, so how do you find? So we need VSD and we need overvoltage. The overvoltage we already found. The source to drain voltage will be the known source Vs given, which is 5 fixed, which is this value, right, minus the V drain, that is vary, right? First it's 4, then it's 2. So each time you change this calculation and you come up with a different value, you compare this to the overvoltage and then you determine if it's triode, or, if it's the triode region or the saturation. And at various values you calculate the drain current as shown by this formula or by this formula. Okay, so you see that as this voltage gradually decreases, the device goes from being in this triode region to the saturation region, right? And the current in the device gradually increases from 350 to saturation value 864, and even in saturation it keeps going up slightly. Okay, so I hope you can follow this logic. Let me know if you're having trouble, but I think it should be straightforward. Okay, next problem 539 is an example. Okay, and now we have actually entered the very last section in this first half of this chapter. So we are looking at MOSFET circuits at DC. Remember, I told you all this is about biasing or finding an operating point for the transistor, which means basically finding a certain value for the these resistors that connect the device to the supply voltage, so that we get a certain desired value for VD and correspondingly ID. Okay, so all the problems in this section are about that, finding those resistances so that we arrive at a known combination of the VD, which basically means the drain to source voltage for an NMOS, or a source to drain voltage for a PMOS, and the corresponding ID. So obviously the gate to source voltage also plays a role here, and so the problems that we solve will tell you how we deal with them. So there are 5 problems in this section. I am not 5 examples shown in the textbook: 5.3, 5.4, 5.5, 6, 7, 8. That's actually 6 examples. I'm only going to pick 5.3 and 5.8 to talk about even, but I do expect you to go through the remaining, because each one of them has a unique problem. It's similar to actually what we did with BJTs, but in unique situation, and you should know all of them. But because they are solved and I don't have too much time to go through every one, I will only solve a few, or we talk about a few. I also have 2 more related to the same issue, but these are problems from the back, 554 and 553, and I will pay a little more attention to these 2. Okay, and then we move on to the next lecture. But so there's a total of 4, 2 examples and 2 problems. So let's quickly go through them in the next 6 to 8 minutes so that you're not late. Okay, so here we are given a very simple circuit with 2 resistors though, okay? So that, and 2 supplies. So there is a VSS, a source voltage, which we have seen for the very first time, a source battery, which is minus 2.5, and then we are seeing a drain, which we have already used to, at plus 2.5. And of course, fortunately the gate is grounded, so that makes things a little bit easier. So all the rest of it that you expect, like for example the V threshold, the mu0 COX, which means the K's, the length, the W, they're all given. It also says, luckily, neglect the channel length modulation, so lambda can be made 0. All he wants us to do is find RD and RS. Okay, so you can see how this problem is solved. I hope not to spend too much time, but let me at least get to that problem. 5.3, yeah, here it is. Okay, so how does he solve it? RD, by now you should know that the technique to use is our simple KVL equation, and he comes up with 5K. To find RS though, it's a little more difficult, and we need to know the voltage at the source, which can easily be found as VGS. So we know this, but we don't know the voltage at this point, right? If we knew this, then we can find RS. So, but we can find this because we know this, and this is at ground. So there's another way to find that, right? So what he does is we find VGS. This in turn can help us to find VOV. So first he finds that this is in saturation. So he uses the saturation formula. Then he substitutes the given drain current value, which is 0.4. I think that value is given, so that's helpful. And also the fact that the VD is 0.5. So using all this, it's not difficult to find Vs, which is what he does. Vs is also VGS, right? So yeah, VGS here, ground to source. So that VGS is 1.2. He uses that here, the negative of it, of course, and then he uses another KVL for the bottom portion, and he comes up with 3.25. So I think this is a pretty straightforward application of the basic KVLs and the drain current formula for saturation, and you should be able to solve this problem. The next problem is pretty interesting. In fact, I would say this really gets exciting here. But if I spend time on this, I won't have time to spend on my 2 problems. So what we'll do is I will let you look through the 2 solutions, because these I feel are quite easy. Problem 553 is a voltage divider. But the voltage divider is used to bias the gate. The one important thing that I may have not mentioned so far, but is really helpful in solving problems, is the fact that the gate current in any MOSFET is always 0. So nothing flows in here. So this voltage doesn't get affected at all, and so the voltage here never goes in. So the fact that the gate current is always 0 is very helpful in solving a lot of problems. And as you look through this, you will find that with that fact, finding RD, RS. Now remember, this example is for NMOS, but he says give me RD, RS and these 2 values using how he solved this problem in figure 5.24a, but for a PMOS circuit. So some things are flipped, and I show you in my notes how to do it. Look in my PDF. So that is one problem. This is another one also, which I think is pretty easy. So let's not spend too much time on that. But let's look at this because this is a little bit exciting. Here, this is exciting because once you learn this, we are jumping, as I told you, after we finish this chapter, we jump to chapter 13, where we actually start looking at digital circuits, logic circuits implemented using MOSFETs. Okay, so using CMOS logic, how to implement digital circuits, AND gates, NOR gates, inverters, all that good stuff. This example actually doesn't tell you that that's where we are going, but if you understand this, a lot of what we'll do in chapter 13 will become easy. So it's kind of an introduction to what we'll do later. Okay, so enough about that. Let's first try to solve this problem. So what he says is there's two transistors, an NMOS and a PMOS, and they are matched in every way, meaning these factors, the process factors, are identical for both of them and they are 1. Also, he is telling us that the threshold voltage VTN and the VTP are also 1. So assuming everything is identical, and also the fact that we can safely ignore the channel modulation effect, channel length modulation, he says find the drain currents IDN, IDP, IDN and IDP. That means this current in this FET and this current in this FET. This is a PMOS FET and this is a NMOS FET. So find the drain currents as well as the voltage VO, the output voltage. Okay, given I input to be 3 different values. So first he is giving us a 0 volts, then he is giving us a plus 2.5 and he is giving us a minus 2.5, which happen to be the same as the biasing battery voltage. So you might recognize that this is a digital low and this is a digital high, right? Of course this is a negative, so there's an inversion effect, but this is how he is asking us to solve to get these two drain currents and the output voltage. Okay, all right, so let's see how he solves this by looking at his own notes, and this is 5.8. I know I'm running short of time, but hopefully this won't take more than 3 minutes, so I'm not too late. Okay, so there are 4 steps, right? First, the basic circuit is shown, then the circuit with 0 volts, the circuit with 2.5 and the circuit with minus 2.5. So the trick here that he shows us is that when you apply 0 volts, everything is symmetrical. So basically, if you just calculate one drain current, you know the other also, which is 1.125, right? And because everything is symmetrical, this V0 stays at 0. Thus both are operating, and so V0 is 0. Okay, both are operating to cancel each other out, so that is 0. Now what's more interesting is when this is a plus. So when you apply a plus biasing voltage to this combination, you're actually cutting off one of the transistors, right? Because we know that a plus gate only turns on an NMOS FET, right? Because you need positive bias at the gate for an NMOS. Similarly, when you apply a negative bias or negative voltage at the gate, what happens? The NMOS turns off and only the PMOS appears in the circuit, right? So what happens basically is by applying a plus 2.5, you are only having to solve an NMOS circuit, and when you apply a minus 2.5, you are only solving for a PMOS circuit. And because the voltages, the supply voltages are a nice plus 2.5 and a plus minus 2.5, basically what happens is you have a plus 5 volts being applied across the gate to source, right? In this case it's a plus 5, plus 2.5 minus or you can see that this is a delta of plus 5 volts, and similarly here it's a delta of plus 5 volts or minus 5 volts. So the gate is at plus or minus 5 volts depending on the connection, and using that information he tells us to use and both these are in the triode region, by the way. They never go into saturation. So he makes that point also. So knowing that fact, we use the triode region formula, and he solves for IDN in this case, and IDN in the next case. And so here IDN is 0.244 and V output is minus 2.44 volts, and similarly IDN here is 0 and IDP is 2.44 and V0 is plus 2.44 volts. Okay, so go through this exercise and see if you can follow along, and if you have any questions, let me know. Okay, so I know we ran over time, but these are important materials, so I hope you followed, and we will continue with the next section in my next recording. I'll stop here. Thank you.